Light years away, 3 numbers, and only 3, are sufficient to define them completely. On the one hand, this makes black holes seem like very simple objects. Only 3 parameters are necessary to classify them: their mass, electric charge, and angular momentum. Know these 3 numbers, and you have everything. And yet, there are an enormous number of ways to form a black hole. They can be formed by gradually swallowing up dust and gas over billions of years. They can be formed by the direct collapse of a massive star in a Type II supernova. Perhaps yet another could grow through repeated mergers of other black hole pairs. We can even imagine a hypothetical black hole formed from the contents of every encyclopedia and electronic databank of every civilization in the universe, every piece of information and every single number ever thought or said by anyone ever. Anything and everything in the universe can go into a black hole, and yet, once it is formed, all of that information is reduced to 3 numbers. How the black hole was made, and what went into it, becomes almost irrelevant. And so the question is, given this almost uncountably large number of possibilities for making a black hole, how can they then be described by just 3 numbers? Where has all the other information gone? Has the black hole forgotten about its origins, or does this information survive in some hidden form? Just what is inside a black hole? And what could it mean for the rest of the universe? Where are you really from? Many of the atoms that make up who you are can actually be traced back to the very first second of the Big Bang, 13.8 billion years ago. It is fascinating to trace our origins. And that's why MyHeritage is such a fun service to sign up for, our sponsor today. MyHeritage makes it fun and easy to build your family tree and discover your origins, and you might also find new relatives. My family is a mix from all across the British Isles, but I was still surprised, for as soon as I typed in my father and mother's name and birth dates into their amazing smart match system, it connected my family tree with someone in Australia, which revealed waves of relatives I never even knew about. So within 5 seconds of logging on, my family tree already had 72 people. And as well as this, I matched with someone on my father's side that opened up whole new branches of cousins in the US. My family was more widespread than I thought. And this was possible because MyHeritage is a worldwide leading family history service, and they have more than 20 billion records available. Indeed, here is an image of my great-great-grandfather I had never seen before. And as a bonus, you can even enhance and colorize old photos like these to bring your family back to life. So, sign up for a 14-day free trial and enjoy all the amazing features MyHeritage has to offer. Thanks to MyHeritage for supporting educational content on YouTube. Dark stars. In the 1780s, the position of a country priest in the Church of England was not especially demanding. A large house with a decent income, a group of servants to do the household chores, and younger curates to take services and visit the sick. To those who wanted it, a life of lazy leisure was on offer. But to those who wanted something more, there was time to think deeply about the world around them. And this is how English parson John Michell spent his time. In the 1780s, Michell had a pretty good idea of how gravity worked. A century earlier, Isaac Newton's theory of universal gravitation had shocked the scientific world. Gravity, Newton argued, was a universal force. Anything that had mass gravitated, pulled instantaneously on everything else. Nothing could avoid the force of gravity, not even, Michell mused, light itself. For, as well as thinking about gravity, Newton had also argued that light consists of tiny individual particles, little atoms of light, which we would now call photons. If this theory of light as particles were true, and gravity was universal, then gravity should be acting on these tiny particles of light, tugging at them and pulling them back. Michell also knew that light traveled fast. Very, very fast. Indeed, earlier in the 18th century, the astronomer James Bradley had measured the speed of light, and measured it well and accurately, through thinking about the aberration of light from distant stars. As the Earth moves through its orbit, the vector combination of the velocity of the Earth and the velocity of light changes. Just a tiny amount, but enough to change, slightly, the apparent location of stars in the sky. Through this, the speed of light was known to be around 180,000 miles per second. This was fast, but not infinite. And finally, intuitively, Michell knew that an object thrown upwards would fall back down. But if thrown upwards fast enough, this does not happen. Instead, it has enough speed to escape the Earth's gravity and reach space. The threshold value, known as the escape velocity, is the minimal speed of vertical launch required to escape a planet's gravity and reach infinite space. It is an easy calculation in Newton's theory of gravity to work out this escape velocity for any given planet and how it depends on the size and density of the object. The more massive the object and the denser it is, the bigger the escape velocity. For the Moon, this escape velocity is about 2.4 kilometers per second. For the Earth, this becomes about 11.2 kilometers per second. For Jupiter, just under 60 kilometers per second. And for our own Sun, roughly 617 kilometers per second. But imagine an even denser body. What, thought Michel, about a body which was sufficiently dense that its escape velocity exceeded the speed of light? For such a body, light emitted from the surface would not be able to escape. In this case, such a body would appear as gravitationally massive but entirely dark, trapping even light under the pull of its gravity. The language and argument here is that of the Newtonian physics that would be replaced by Einstein's theories, but the concept it is describing lives on and is clearly recognizable. Michel's work was, although the actual name would not be used for almost 2 centuries, the first description of what we now call a black hole. Michel was way ahead of his time, and his results seemed no more than an abstract curiosity. It therefore went into the scientific back drawer and stayed there for 150 years. And the next time this drawer would be opened would be in the miserable trenches of the First World War, where the German astronomer Karl Schwarzschild, desperate for an escape from the hellscape surrounding him, pondered the equations of Einstein's brand new theory of general relativity. Having developed his special theory of relativity in 1905, 10 years later Einstein succeeded in extending it to include gravity, constructing his general theory of relativity. This theory requires 10 equations to describe it. These are now familiar, but when first written down they looked formidable and almost impossible to solve. In 1915, the ways into these equations were unknown. Trying to solve them, Schwarzschild looked for the simplest possible solution he could imagine, a spherically symmetric spacetime around a concentrated point-like mass. Plugging everything in and calculating carefully, he obtained a solution, now known as the Schwarzschild solution. This is probably the most famous solution of Einstein's equations. Schwarzschild solution involves one parameter, a uniform spherical mass. In general relativity, mass deforms the nearby spacetime. The magnitude of this deformation depends on the radial coordinate. The closer to the mass, the bigger the deformation, while far away there is little change. The Schwarzschild solution has one deep and striking property visible in it. As the distance from the mass comes in from infinity, there is a critical distance where something strange happens. Some terms in the solution appear to go to zero, while others go to infinity. What did this mean? Although it was not possible